Sorry. Welcome to everyone. This is the continuation video of after the knowing the applications of the control systems in power electronics, power systems, and mechanical systems. So that means machine systems. So now we already saw where how which are the equipment, which are the things how we can able to control. But to control that one, what we exactly we need is you need to remember one thing is all the controllers will only understand the mathematics only. So that we, because of that thing, so whatever the equipment is, that equipment, whether it can be a electrical equipment or a mechanical equipment, or it will be electromechanical equipment also, or electro rotational whatever equipment also, we need to convert this entire system into mathematical modeling. Okay, so that is our today's topic. So that is mathematical modeling of the physical system. So the topics to be covered in this total lecture will be types of mathematical modeling. There is a multiple mathematical modelings are there, so which are that one, and how in this lecture what we are going to discuss, we will discuss only the mechanical system to electrical system. We will discuss step by step. So that's why I'm disconnecting every video with respect to system to system variations. I'm clarifying clearly. Okay, and the next one is here, if you see this one, so mathematical modeling having a first, I'm discussing as I said, it's a part one as a mechanical system. So here, to know, if you see that one, the mathematical modeling completely is done with respect to the total three type of modelings are there. That is differential equations, transfer function, and state space equations. Okay, so because of that, these three can able to convert the any mechanical system into a mathematical modeling. Once the mathematical modeling is done, that will be easy to feed to the controller and to make the system to be controlled and the actuator to be which especially which one to control, which one not to be controlled. That each one that decision can be easily understand when we get the mathematical equation. Okay, so that is how we I already here I read as a they can help us to predict the behavior and also which one to optimize the performance and also which control parameter we need to control. For example, sometimes we can control the voltage, sometimes we can control the current, sometimes we can control the any other equipments also, like speed or pressure or whatever vibrations, noise, anything can be controlled. So we need to understand what exactly the parameter is affecting that one. Then only we can easily understand that one. So that error or that effect will be is a reflects in the mathematical form. Okay, so now the basic mechanical system, what we already have, which is already we know from the very ages. So that is basic mechanical system is having a any mechanical system we have the mass, that means a mass of the total entire system, and the damper which relates to the it's a friction, that means how much movement it is having, that is what we want to see, that is that one. So that is called it as a damping factor, we'll call it. So in that damper is identified or represented in the one indication as a B, and the spring which represents the elasticity force, because every mechanical will have some force will be there. If when the force is applied on one mechanical system, either it can move in vertical or horizontal or rotational or backward or whatever it will be, so that will be happen. So because of that things we need to consider all these three, because when you get these three things, then only we can able to understand or we can able to convert the entire mechanical into a mathematical modeling. Okay, regarding that thing, the most important one what we need to understand is the Newton's second law. Okay, the Newton's second law, that is F equal to ma. So here the acceleration will be converted with respect to the velocity, so or force or whatever it will be. So that's we are considering as the d square x by dt square. Okay, using this equation only we can able to write the motion of the spring or motion of the system, whether it can be whatever the system it will be. Okay, so this is very much important because from now onwards this f equal to ma will show many places it will be reflecting that one. Whenever the mechanical part is even whatever the simple small part is also included, then automatically it will come into picture. So we will see one basic example. If you see here, the basic example will be like the mass, damper, and a spring is there, and f of t is the output, and z of t will be the that function. Okay. So if you see that one basic spring, damper, mass system I took. Okay. When I convert this entire system into mathematical modeling, as I said, like it is f equal to ma. right? F equal to ma. I need to write first with respect to this. Okay, so m with respect to m d square x by dt square, and the whatever the damper is there, the damper will be written with respect to b dx by dt will be there, and also that whatever the k will be there, that k will be not having anything, no differential will be there, it is having a normal constant, that is called as the kx. So f of t. So whatever this f of t is there, that means here the every term is represented in the t domain. That means the time domain, it is there, it is already always all in the time domain, but we need to convert it to mathematical. So to understand the simplification, so that's why we convert the time domain to the S domain analysis. That is called it as a Laplace domain. So to convert that one, we need to apply the Laplace transform to the above equation. That means this equation. So then automatically we can get the S domain equation. But here what we are taking one assumption is, assumptions are very much important in the control system. So first basic assumption is the whatever the initial condition, it is starting from the zero, it is not having any before initial conditions or after initial conditions. So that's why the initial condition are always considered as a zero only. So when we apply that one, d square x by dt square will be converted into s square of x of s, and dx by dt will be converted into s into x of s, and x of s and f of s. So when x of s to the x of s, this will be the transfer function to the entire the damper spring constant, then this will be the final damper transfer function with respect to this one. Okay, so then according to this, whatever we need to control, we can easily get the equation. So we can get the numeric denominator dividing factor. So we can easily get which one need to consider, which one need to control. Okay, this is how the transfer function will be happen with respect to displacement and the input force. Okay, so this is the mechanical system, purely mechanical system to electrical system we are converted. Okay, the mathematical representation with respect to the electrical. So to next in the next video we are going to see some rotational part of that one, so that we are going to see in the next video. Thank you.